we are very happy to have Michele Del Zotto, who is going to tell us about exploring the higher structure of symmetry. Please start.
Turn it on.
Yes. Yes.
Is it on now? Okay. Thank you. So first of all, let me thank a lot all the organizers for putting together this meeting. It's a pleasure to be here. It wasn't as easy as I thought, but it's really a pleasure to have this opportunity to see you and meet you in person and visit Japan. It's really fantastic. Thank you very much. So today I will talk about some exploration of the higher structure of symmetries, which we started together with Kantaro and other collaborators, Christian Coppetti and Yifan Wang, about a year ago. This project has a follow-up that I'm working on together with my student, Elias Riedel-Gorning, and my postdoc, Shani Mainet. And also another applications of the higher structure of symmetry that appeared more recently last month, together with the same Mainet, Shani Mainet, Daniele Migliorati, who is another PhD student in Uppsala, and Kantaro. So the mantra of several talks and this conference is that symmetries are associated to topological membranes. No? Symmetries of a quantum field theory are associated to regions where the quantum field is discontinuous, and these regions, we can model them with some topological membranes that leave invariant all the correlators and all the possible operators insertions. No? So these topological membranes they act on operators, well, we know they act on operators by linking or by crossing. And they provide generalized quantum numbers for the extended operators. Now, topological membranes can form intricate networks by forming junctions of various kinds. And these are also topological and give to the symmetry the higher structure. Okay. Now, the higher structure of the symmetry acts on extended operators and acts on correlators, but it is subtle to detect. Okay. That is why it went unnoticed for so much time, I think. In order to detect it, one needs to use either a non-trivial topology for the spacetime, or extended operators in correlators. And these two are somehow synonyms. I mean, inserting a line is sometimes equivalent to carving it out from space and assigning boundary conditions to the fields. And so extended operators and topology of space are somewhat a concept that go hand in hand. Okay. So it has, however, it's subtle to today, but it has profound consequences. Profound consequences in terms of selection rules, in terms of anomalies, in terms of constraints on RG flows. So in my talk today, I will explore some of these, some of constraints on RG flows that arise from having a symmetry that has a higher structure. And the star of today's talk is the non-invertible symmetry in massless QED. Non-invertible chiral symmetry, which because of the ABJ equation is non-invertible. This is the one form magnetic current. So we've learned by several works over the past couple of years that there is a way of rescuing this symmetry in terms of a topological membranes, of a topological membrane that we denote dp. It's a three-dimensional one, so the support is a three-dimensional surface. And this topological membrane has the following form. It has a factor, which is like the generator of the chiral rotations. And this factor is stacked with a word volume topological field theory. So, sorry. This one is a and this word volume TFT is crucially coupled to the magnetic one-form symmetry, meaning that on the word volume of these defects, there are lines, line operators, which are topological lines for this theory. But they are also endpoints, end lines, if you like, of magnetic one-form symmetry topological defects from the bulk. Okay. So this is the meaning of this decoration of the TFT. No? So we have to end magnetic one-form symmetry along the lines inside of these defects. Okay. Now, of course, the reason why we can compensate for the anomalous shift here comes from the fact that in this theory, the line braid and the charge assignment here is such that when I braid two lines like this, I pick a phase and because of this braiding, we can cure this effect thanks to this coupling. So whenever there is a problem arising from the ABJ equation, the lines and their interaction with the magnetic defect compensates for that in the bulk. So in the paper, in the first paper one in the references, we have studied the possible structures of morphisms of this symmetry of this kind. So when working with topological membranes, like morphism are what replaces the group multiplication, or what replaces the way in which we work with group elements of the symmetry usually. No? So we computed these in one. And we found that the Higher structure is encoded in engaging interfaces. So, oftentimes, when we take two of these defects and we stack them on top of each other, a collection of lines becomes neutral with respect to the bulk. So because of just how charges are assigned, it can happen that they become genuine lines inside of the three-dimensional theory that do not have an avatar in the bulk. And when that happens, then we can gauge these lines. We can gauge them away. And this gives rise to the interfaces that correspond to these morphisms. Okay. So we can detect this Higher structure with partition functions on curved spaces. The simplest example is that we considered in that paper is S2 times S2. So it is kind of instructive to see this example if you haven't seen it, but I'm sure that some of you have already seen it. So by rise of hands, how many of you have seen how to use the Higher structure to constrain this partition function? Oh my God. Okay, so maybe I can make a little detour because it is kind of interesting. No? So, well, there is a little exercise to visualize S2 times S2 on a plane. Okay, so this is a trick I learned from a book in topology. In order to visualize a four manifold, you can think of it as if it is a movie. No? So like if you want, for instance, so you know how to visualize a three-dimensional manifold, we can draw it. No? And then if we draw the future and the past in different colors, then we can kind of visualize a four manifold. So for instance, if you want to visualize a product of planes, say, you want to visualize two intersecting planes in R4. So in white, I draw the section, and maybe we can draw the future in blue and the past in red. And so you can see that this is a way of kind of visualizing two intersecting planes in R4. Okay, so S2 times S2 is similar. The way in which we visualize it is the following. So in order to visualize S1, we know that we can draw an interval and identify the points. Okay, so S1 is an interval with endpoints identified. No, S2 we can view as a S1, which is fibered over a line. No, something like this. It shrinks at the two endpoints. Okay. Now S1 times S2, a bit harder, but the idea is the following. We use this description of S1, and so we draw an S2 in the interior, Then this is S1 direction. Then we have an outer S2. No? So you see, like this is S1 times S2. No? S1 is this interval with the endpoints identified. And for every point in this interval, there is a copy of S2. No? Okay. Only when we hit the boundary inside, we come back from the beginning because we have identified these 2 points. Okay. So now if I have to do S2 times S2, okay, then I draw in time. In time, this interval shrinks to a point, and this interval shrinks to a point in the past. Okay. We have a drawing of a 4 manifold. However, doing the manipulation that I want to do with this drawing would be impossible. So let's do it with a simplification. We draw like this. Just a section of this 4 manifold. Okay, this is the inner S2, this is the outer S2. Okay. So when we have a manifold like that, we can bubble out a topological membrane on a sphere, on a 3-sphere. No? So in this drawing, we draw it like this. There is a little round sphere, and this is dp over n bubbled out over S3. Okay. However, now we can exploit this topology. This comes at a price. Now we have to divide by the partition function of the TFT on S3. So this is why I have this factor. I insert it on this, on an S3. And now by a simple manipulation, I can just take this through the 2 boundaries. Like this. This one is going this way. This one is going the opposite way. Okay. I just took this S3, pushed it against one of the two walls, and it came in from the other one. Okay. But now you see these 2 guys have opposite orientations, and since they are topological, I can make them come together. No. When they come together, I get one of these morphisms, and in this case, it is just the morphism between the defect and its oppositely oriented version. Okay. So when that happens, we produce a condensate. So, okay, this one is going this way, this one is going that way, and here we end up with a condensate. Okay. But I'm using the fact that let's do the simplified version to avoid problems with normalization. This is equal to this. And this red gadget is a condensate of this one form symmetry. Okay. So now here there are endpoints where this one form symmetry, this condensate of one form symmetry touches the topological membrane, and at these endpoints we have lines. Okay. So there are lines here and there. And now, if we take this back into this 4-dimensional space, this is just one line wrapping a circle in this 4-dimensional space. But here we just see 2 points. One is ingoing, the other is outgoing. Okay. Now we can perform the same manipulation here. Now what we do is we just move it like this. This is topological, so we can do this kind of manipulations. No, so and don't forget the normalization. Okay. So you see, I just took some parts, I bended them, and like it's topological, so we can do it. And now again, here we have the collision of 2 oppositely oriented defects. And what we obtain is another condensate. We'll go like this now. So here we have L and Cn. And here we have L prime and Cn prime. Okay, and then there is the normalization. But now you see, we can exploit the topology once again, because this is topological. So we can take this inner circle, push it against the inner sphere, and when we do that, it will emerge from the outside. Okay, so we push it, it emerges from the outside. And when it emerges from the outside, we get this figure. Here is our condensate. Here is the line L. But now the other one is stretched in the other way. Okay, so we get to that picture. Now this one is again an S3. It's a closed loop in this diagram. So it's the way in which we describe an S3. So we can shrink it back to 0. No? When we shrink it back to 0, we have to pay a price. Sorry, we have to pay a price, which is related to the fact that the line L prime and the line L are now braiding. And so when we shrink it back, we pick up a phase from the braiding of the lines, and we remove the normalization factor. So we end up with something that looks like this. It's a sum over all possible, well, there is a normalization factor coming from the condensates, and a sum over all possible line defects. And the phase that comes from the braiding of the lines goes like this. And then here, we are decorating with all possible ways, all possible eta defects. So here we have eta 1 magnetic B over N. And here we have eta 1 magnetic C over N. Okay. So eventually, the equality that we got by this topological manipulation is this one, that partition function of on the product of S2 is equal to this one. Summed over B and C in the n, 1 over n. No? So this is an example of a word identity that comes from topology. Okay, we just used the topology and we found this word identity. Remember that these defects, they are also the same as the duality defects. So if you just have one duality defect of a given kind, you get an identity of this form. This is kind of expressing the fact that the theory is self-dual in that case. But for QED, we have infinitely many of those. We have infinitely many of these relations, and they are just the expression of the fact that in QED, we can shift the theta angle as much as we want. And we obtain results that are related one another by a shift, a rotation of the theta angle. Okay. Yes.
I try to understand
Yes.
what is going here.
Yes.
So here in this expression, you are referring the zero form symmetry by D.
Yes.
The zero form
Yes.
non-invertible symmetry
Yes.
in the massless QED.
Yes.
Okay. And then there appears a factor of the topological field theory there, A3.
Yes.
Yeah, and it refers a three-dimensional surface, sigma 3.
Yes.
And then you next consider the intersection in between that sigma 3 and two-dimensional surface, sigma 2, that supports the symmetry operator of the one-form symmetry.
Yes.
Ah, I see.
This is happening because these lines of this they are coupled to the one magnetic one-form symmetry, and so they are not just genuine lines. They are endpoints for these one-form symmetry defects. This is another way of saying that there is this equation.
I see. So my question is that the configurations you put in these figures of the sigma 2 is somewhat arbitrary?
It's not. It's dictated by the topology. No?
Topology.
Like I'm hiding the topology because I'm drawing just a section.
Oh yeah.
But whenever two of these guys collide, no, we have to perform a surgery operation on the different volume, and so the topology is a solid torus.
So, for example, when you write down this figure, and then this configuration with sigma 2, it is just some starting point.
This is not sigma 2,
Not sigma 2.
No, this is the condensate, which I erased. But when you fuse D with its opposite, you get a condensate. No, I had an equation on this board.
But it refers to some two-dimensional surface?
No, it's a fusion of two three-dimensional things. No? So it is. I wrote it as a condensate, Cn. No?
I see.
This condensate is still supported on a tree on the same tree manifold.
I see.
No.
Okay.
But it is made out of only of these defects. So you take the three manifolds and you decorate all its two-dimensional cycles with these defects.
I see.
And you sum over all possible ways of decorating them. And that's how you define this operator. So when this summing is the reason why I get this sum.
So
here I'm just expanding the definition of the condensate, exploiting the fact that there are only two cycles in the game, these two spheres. Okay.
Okay.
Yes.
Thank you.
Yes. Sorry. Yes. Here, because the blue defect, I can bubble it out of nothing, and I can shrink it to nothing. No. In this topology, this is what I've done. No, I bubbled it out. I exploited the topology to fold it around, and like since it has an non-trivial higher structure, by folding it against itself, I get some non-trivial topological defects out of it. No, and this is the outcome of this. No, this was just a yes. But I said no. There are two ways of detecting it: non-trivial space-time topology or insertion of extended operators. This is non-trivial space-time topology. No, of course I can insert operators here. No, in this correlator I can insert operators on S2 times S2, and when the topological membrane crosses them, it will act on them, and it will modify this identity according to how it acts on those operators. No, this is just the easiest such word identities. Okay. Yes. Yes, I just copied it back there because I thought that they couldn't read behind this corner. Okay.
I have another question. So this fusion is not the usual fusion rule, but it's partial fusion. So you may have non-trivial coefficient like F symbol, right?
Yes.
Do you know the value of F symbol in this special?
In this case, there is no, since it involves the defect and it's it's dual, there is no F symbol. But in paper 1, we compute explicitly the F symbol in this case. It comes from a diagram. So the F symbol is tracking the associativity.
Yes.
No? So it measures the difference between a fusion of this kind, no? And the other one. So it would be something like this, no? And so you can take these two diagrams together to compute the F symbol. You can compute the trace of it. You can glue this on that and form some sort of a bubble. So this is something that I learned from Kantaro. No? And in 2D theories, this is a number. If you do it with these topological membranes, they are three-dimensional. And this one is a two-dimensional gadget. If I shrink it down, I get to a point. And this is a two-dimensional object. We computed it explicitly for these defects using these fusion rules. And we found that it is a two-dimensional. So the F symbol here is a two-dimensional TFT enriched in, in generators of the magnetic one-form symmetry. You cannot read. Sorry, I write it again. Yes. So it is a two-dimensional TFT, and we can determine it exactly. We can compute exactly what is its structure, and also we found out that it is has consequences on correlators because of the way in which these defects act on extended lines. If you take a line and move it across the F symbol, it detects a correlator of this two-dimensional TFT. And so it's the Higher structure is really acting on the operators. It's not something that is just nice mathematics. It's also has consequences.
Thank you very much.
Thank you for the question. It allowed me to mention this. When we compute the F symbol, this is another very good question. It depends on the choice that we make here. But the way in which it depends is related to TFTs that are decoupled from the bulk. And that somehow gives an equivalence relation. When you build your topological membranes, there is some sort of gauge equivalence, if you like. You can always stack with TFTs that are decoupled from the bulk and get rid of them because they are decoupled. But the choice that you make is like a gauge choice. So once you make it, you commit. No? And all the results on the observables will be eventually independent of this choice. But once you have made it, you commit and you stick to it. And in this paper, we choose this, the minimal one. But of course, if one wants, one can work with another one if it is more convenient. Yes. That one. It's interesting. We believe there is a correspondence with Bordism theory. So you can represent four manifolds as Bordisms, and they are like Bordism of the zero manifold in 3 dimensions. No, it's a compact four manifold, so it goes from nothing to nothing. No, and like you can view the addition of various types of handles to the four manifolds as morphism in the Bordism category that we should decorate with elements of the symmetry category or with topological membranes, and morphism between them induced by the way in which the handle gluings are going. It's tricky. We discuss it in the paper a little bit, but we believe it generalizes. Like the philosophy is the right one. Yes.
Do you expect to have that you can extract different information between spin structure and the fixed scheme?
We believe there is a in the paper we only work with spin manifolds, but there is a dependence. There is a dependence in the TFT can detect subtle. Here we don't have it exactly. Yes, but there should be, and it's something that can be worked out that we haven't. It's an interesting question. So now the question is, so we have this structure. It's rich. No, can we exploit it to learn about RG? So we know that in four-dimensional theories, the presence of one-form symmetries detects confinement. No? It's, if the infrared, the one-form symmetry is unbroken, then the theory is confining. So this is suggestive of a classification of phases of gauge theories. It was suggested already in the first paper on the subject. This is this paper by Gaiotto, Kapustin, Seiber, and Willett. And especially for this question, there is also a very beautiful paper by I think Zohar is involved. I don't remember all the authors. I think Gaiotto, Komargodsky, Kapustin, and Seiberg on the theta angle. However, in this case, we have a symmetry that mixes one-form symmetries with zero-form symmetries, and so it is natural to expect that it plays a role in the context of these questions. So there is an intriguing scenario that we want to exploit to make use of this, which is called a dynamical Abelianization. So dynamical Abelianization, there is a non-Abelian theory that gets approximated by an abelian theory above the confining scale. So this was proposed by 't Hooft in 81, I think. And so since it is an abelian theory, then it can give rise, if we choose it wisely, it can give rise to something similar to what we observed in massless QED. No? So as a model to play with this, we chose adjoint QCD in 4 dimensions with 2 flavors. But in general, well, adjoint QCD in 4 dimensions with F flavors is something that has a Lagrangian like this. It's a 4G. And then F mu nu A, F mu nu A. And then there is a sum over the fermions. Weil fermions, derivative Weil fermion. No? Something like this. And so this is interesting when F is less than or equal than 5. So this 5 above, this is IR free. Four, 3, 2, 1, 0. So here, I think it is believed that this theory has Banks-Sachs fixed points. So it is gapless. And below is confining. So this one is Young-Mills. This one is n equal to 1 Young-Mills. And this one is our friend here. So for this one, for n equal to 1 Young-Mills, there is a proof. Cybergwitten. Have a proof that this theory is confining. And for this case, there is a very nice work by Cordova and Dumitrescu. And a series of follow-up by Docker, Dumitrescu, Gershkovitz, and Nardoni, which are about exactly this idea of using dynamical abelianization to study the phases of this theory. And this is the case that will be of interest for us, no, in this game, because we'll exploit what we know from this paper to recover an abelianized phase where there is a non-invertible symmetry. So, oh, good question. Bet the answer. Maybe some expert in the audience can give a better answer. It's still confining. Oh, good. Thank you, Zohar. Like this. Yeah, these are all conjectures. No. Maybe this one is not, but otherwise I think they are all conjectures. Thank you. So for f equal to 2, we have adjoint QCD. And as Zohar just said, by Gaugino condensation, it is expected that the flavor symmetry breaks to U1. And there is a U1R symmetry, UV U1R symmetry, which is a non-abelian ABJ anomaly. So this is something that we cannot fix so far. It's topological membranes. And it's broken to Z for NC, which by Gaugino condensation is also broken to Z4. And so the IR phase is believed to be a bunch of copies of CP1. And because of this breaking, there are NC copies. In the paper, we denote it like CP1 disjoint union NC. Okay. Now, dynamical abelianization arises from softly broken Cyberwitten theory. And we can use it to argue for this. And the idea is that here, we see that CP1, this CP1, some beautiful work by Chen and Tanizaki and Xin, has a non-invertible symmetry. Exactly as massless QED. The same structure. Same fusion rules, same structure. So there is a question: can we match it somehow with the abelianized phase? Is there a way of matching? So with n equal to 2 Cyberwitten, so the idea is the following: no, adjoint QCD has a cousin which is n equal to 2 Super Mills, which is obtained by taking this adjoint QCD and adding an adjoint complex scalar phi. Then we have that phi and the chiral fermions form an n equal to 2 vector multiplet. There is no clock. There is a clock. 12. 12, okay.
I don't understand what you're trying to prove.
I want to use the matching of non-invertible symmetries between the abelianized phase and the CP1 phase to track the quantum numbers of the solitons and identify them with UV quantum numbers. And that will happen because the non-invertible symmetry has a higher structure and it is robust in this flow. Thank you. I should have said it. But I was leaving it as a punchline at the end, but it's better if I say it. No? So we want to learn about the RG. So you see, there is a flow. There is a flow. If I take this n equal to 2 Super Mills and I send the mass of this phi to infinity, I end up with adjoint QCD with the 2-pi flavors. No? Here, however, we know that by giving a non-trivial VEV to phi, can get to the Coulomb branch. So we break SU and C to U1 and C minus 1 by a Higgsing. And this is the abelian phase. What Cyberwitten taught us is that in this abelian phase, there are special points in the Coulomb branch where we don't get just NC minus 1 copies of Maxwell theory, but there are some additional particles that becomes massless. And this is crucial. Without these massless particles, there would be no Cyberwitten solution. You cannot build this Cyberwitten curve or the abelian variety that is fibered over the Coulomb branch and captures the effective action without this massless particles. So there are points in the Coulomb branch where monopoles and ions become massless. So picture the Coulomb branch like this. There are points where some particle become massless. Okay. Now, it is interesting to ask whether there are points where more than one dion become massless simultaneously to another one. Some of these points give rise to conformal field theories, when the dion that become simultaneously massless are mutually non-local. This is how Argyres-Douglas conformal field theories were discovered. But there are also other points where the dions that become simultaneously massless are all mutually local. No? These are called multi-monopole points. Were studied by Argyres and Faraghi, and Clem, Lerche, and Douglas and Schenker So well studied. There are NC minus 1 mutually local DPS monopoles. Simultaneously massless. Okay. And there are, so if let's say that these are the multi-monopole points, and there are NC minus 1 of them for SUN C. Okay. So this is a very interesting abelian phase because we have NC minus 1 copies of massless SQED. Because for every monopole point, we can find a dual frame where we describe it using massless SQED, and they are all mutually local. So we can choose this frame consistently in such a way that we just have NC minus 1 copies of massless QED. So this gives rise to another arrow here. No? So we have an arrow that called Cyberwitten. Here is the space of abelian gauge theories. There is a subsec, which is the Coulomb branch. And there are these NC minus 1 multi-monopole points. Okay. Now, so Cordova and Dumitrescu showed that there is a flow that does essentially like this. Okay. So there is a flow that does this. And so this leaves us with some scenarios for adjoint QCD. No? So there is one scenario in which also adjoint QCD has a flow that does like this. Let's call it 1A. There is another scenario where adjoint QCD just flows to CP1, 1B. And then there is a third scenario where adjoint QCD does something else. No? These two scenarios, sorry, are in the same universality class. They belong to the same universality class because they both flow to the CP1 model. Okay. And for NC equal to 2, this was done by Cordova and Dumitrescu. For an NC greater than 2, this was done by there is this cascade by Docker, Dumitrescu, Nardoni, and Gerkovitz. In the paper, we give an alternative argument that doesn't need the cascade, but reaches the same conclusion that they had. So in these two scenarios, there is emergent non-invertible symmetries. Symmetry. No? Because at these points, we have the chiral symmetry. We have the chiral symmetry of massless QED emerges, and then we recover it in the CP1 phase. However, its matching is non-trivial.
What they're trying to match.
Yes.
What they're trying to match.
I will get there. So let's consider the case NC equal to 2. Let's get to the question by Zohar. It's a good. Say I have 4 minutes. And NC equal to 2, So we have a how do we call it? So this emergent non-invertible symmetry, we call it U1X. No, this is chiral symmetry. And U1X acts on fermions that decouple along the flow, along this flow, because of Yukawa couplings of this type. They get masses. But these decoupled fermions can be used to couple the U1X symmetry to the solitons in the IR. Here we have a soliton which is called the Hopf soliton. This is a subtle effect. It's known in the case where we are not in massless QED, but just for a theory where the symmetry is engaged. Abanov and Wigman showed that indeed, so if you have this U1 symmetry, which is decoupled, you have a coupling like this. This one would be a skyrmion number. So let's call these, where do I, let's call these U1s, let's call them U1 magnetics, because they are magnetics. So this is U1 magnetics. And if you have just a theory where you don't have the gauge field, but you have the fermions, it will have a U1M global symmetry, which is the one that you gauge to get to the QED. In that context, you have a flow to an S3. And that S3 has a skyrmion, and the skyrmion acquires quantum numbers with respect to the chiral symmetry in this way. In the case that we are considering, the argument is the same. It's just that the skyrmion, when we gauge the U1, becomes the Hopfion, Hopf soliton. So this is S3, and here we gauge the U1 magnetic. No? So the fermion couple the U1X symmetry to the Hopf soliton via this term, exactly the same term. This is one point. And because of the work by Chen and Tanizaki, we know that the U1X symmetry for the Hopf soliton is non-invertible. Okay. So it gives a candidate to match with the non-invertible symmetry in the massless QED phase that arises in the abelianized theory. Now, moreover, because of the identification in the CP1 of the one-form symmetry with the vortex, so we see that so the Tn one-form symmetry of the UV theory, this one is contained in the U1 diagonal magnetic symmetry that comes from the diagonal of all these U1s in the abelianized phase. No? So this sits into the product over the Cartan of the U1 magnetic. No? So this one has a BJ anomaly. It goes like NC minus 1 over 4 pi times well, this f squared. No. So this one is the one that we want to identify with the non-invertible one-form symmetry here, and that comes multiplying this factor by NC minus 1. So in the case NC equal to 2, it's just the same, but in general, there is this factor that there is a rescale. No? So in particular, this implies that the Hopf-Soliton is has a statistics. So for NC even, the fermion, for NC odd, the boson. So there is a non-trivial theta term in the CP1 model. It was essentially already remarked by Witten in 81. And moreover, if we want to think about an operator in the Abelianized theory that can create the Hopf-Soliton, this operator must have a quantum number that is NC minus 1 with respect to the chiral symmetry. And one such operator is given by the product of the Cartan fermions. One second. So the idea is that
time is already
is over.
Five minutes over. So
okay.
you
Can I finish?
Yes,
can I have 2 more minutes?
Yes, yes.
Okay.
2 more minutes.
So we have a candidate that can create the Hopfion in the Abelianized phase. And this suggests to answer a question that was asked by Schiffman and Bolognesi, whether there is an operator in the UV that can create the Hopfion. No? Is there a UV operator that can create the Hopf-Soliton? And the idea is that such an operator, some sort of a baryon, if you like, for the Hopfion, is just product over all elements in the adjoint of this form. So these are the positive roots, and these are the Cartan generators. And you see, like in the Abelianized phase, when we flow from adjoint QCD to the Abelianized phase, this term here acquires masses, and it acquires masses via the condensation of the adjoint fermions. So this part here is screened by the condensate. And we are left with this product. This product here has the right quantum number to match with this type of operator. And so thanks to the emergence of this non-invertible symmetry and the fact that we have recognized the magnetic one-form symmetry with the one-form symmetry in the UV, so this is saying essentially that vortices carry color flux. No, vortices carry color flux. The Hopf-Soliton instead is associated to baryon-like operators in the UV theory. And we can identify them. This has the right growth, like the Bolognese and Schiffman estimated an energy for the baryon that scales like NC squared. And this one has the right type of scaling in energy because it contains exactly NC squared quarks. So in conclusion, so we see that the fact that there is a non-invertible symmetry, so the non-invertible symmetry has these higher structures. Higher structures are somehow give rise to interesting consequences on spacetimes that have some topology and some insertion of operators. But also when they emerge along RG flows, they give rise to more structure that one can exploit in addition to what is known. No? So in this case, you see like the non-invertible symmetry arises in the abelianized phase. There is a dictionary between the abelianized phase and the quantum numbers of the UV theory that comes from the dynamical abelianization. But because of the emergence of this symmetry in the abelianized phase, we can track the quantum numbers of the abelianized phase down to the CP1 phase. And because of the matching of the higher structure, we can translate the quantum numbers here, the Hopf and the vortex, into quantum numbers of the abelianized phase, which can then be translated into the UV quantum numbers. And this is how we can identify, for instance, a candidate for a baryon operator in this flow. Okay. So yes, thank you. Sorry for going over time.
Thank you very much for the talk. So time has already passed, but maybe just one question, if you have.
Yeah, so this emergent non-invertible symmetry has R over Z structure. So it's almost U1,
yes.
Q over Z. So
yes.
And does that almost continuous symmetry protect the decay process of that kind of baryon? So I'm wondering that, so if this emergent non-invertible symmetry has some physical effect on, for example, on the lifetime of this Hopf soliton?
It's a very interesting question. I think so. Like in a sense, the fact that there is this symmetry allows to track this operator back. No, so we expect this will be there in the IR, and it really it's the operator that creates the Hopf soliton. No, the fact that it creates it, however, is something that we get evidence for only in the abelianized phase. The abelianized phase, we see that in order to hit that Abanov-Wigman type coupling, we need a profile which is the solitonic profile, and that one is the one that allows to recognize no. So it's an effect that like the stability which is guaranteed by the non-invertible symmetry is from the abelianized phase down to the CP1. No, that I would say is robust. No, the other part comes from the fact that there is a dictionary between the quantum numbers of the gauge phase, the ultraviolet gauge theory phase, and the abelianized description. No, that one is more like is like the two abelianization idea. No, so you can recover information about solitonic particles in the UV from an abelianized description. So there are like dions inside protons, if you like. No, yes.
Okay, maybe there are lots of other questions, but please discuss in lunchtime break. And let's thank to Michael again. Thank you very much for